In this video I'm going to be talking about some vector arithmetic stuff that maybe was in your pre-cal class and maybe it wasn't. You know, if you were in my pre-cal, this was definitely part of the first semester. Okay, so I'm going to kind of just give you a quick list of the things that I'm going to go over in this video just so you know what to expect. Alright, so I'm going to start by talking about, how to find the length of a vector. We'll look at the dot and cross product, and orthogonality, and the angle between vectors. It's the same thing. And I'm going to define a normal vector to a plane, which is something I didn't talk about in the first video because I was trying to not use vectors in that video. But this will be a very useful tool for us to, orient planes and really to work with them. It'll really make things a lot easier. All right, so for the length of the vector, I'm going to start with a two-dimensional vector, like something like the vector, maybe 5 and 12. And, maybe I should have done 9 and 40, because those of you that know me know that that's my favorite Pythagorean triple. But, here I'll go 5 over 5, and up 12 would be a little more than twice that. So from here to there. And so I'll draw that vector A. And you can see in a two-dimensional case, it's pretty easy to see why we're going to be doing the Pythagorean theorem. Okay, so the length of A is pretty clearly the hypotenuse of that right triangle. So that's the square root of 5 squared plus 12 squared, which we know is 13. All right. In 3 dimensions, okay, what I'm going to do is I'm probably going to just call it, like x, y, and z or something. So I'm going to just draw a vector, and then I'm going to, actually I'm going to draw the parallelogram first, because I know how my drawings are. It could be risky. I think this would be appropriate. Okay, now the idea with this vector, and I am going to probably draw stuff that, probably, right, about like that. And length of the vector is, I think I'm actually regretting making this a height of just 1. I'm probably going to make it a height of 2, so I'm going to have to just pause and start over. Okay, this will be better for a variety of reasons. Okay, so what I'm going to do is I'm going to say just, suppose we've got a vector that's starting here and ending there. Okay, going diagonally through the rectangular prism. So what I'll do is I'm going to try to make sure I go directly at this. In fact, I think it's important enough that I'm going to try to use a straight edge. Move some stuff, bring this in here. And then we will just kind of lightly draw. So I'll let the light pencil be the vector. Okay, so you can see it's coming from that front near corner to that back far corner. Okay, that's our vector. And what I'm going to do is I'm going to call that vector B. And suppose this is, I've gone to the right by 4, out in the y direction by 1, and up in the z direction by 2. So this vector here is going to be vector B equaling 4, 1, 2. Okay, now if we want to find the length of this, we have to draw it as, like the hypotenuse of a right triangle. So what I'm going to do is I'm going to say, actually, okay, envision this, and this could be a side of the right triangle. Then the third side would be that. I probably should use the straight edge for that too, but it's too late now. Okay, so you see that kind of diagonal along the floor of the rectangular prism is going to be one of our, it's going to be one of the sides of our right triangle. So the length of B is going to be something that we can find by taking the square root of, 2 squared plus this thing squared. And now this is going to be, this length is the square root of 1 squared plus 4 squared. So it's the square root of 17. But then when we square it for the Pythagorean theorem, we realize that actually it's the same as just taking 2 squared plus 1 squared plus 4 squared altogether. Okay? And just think about this more. Or look up on the internet why the Pythagorean theorem works in 3 dimensions, and it works in any dimension. Okay? So this is going to end up being 4 plus 17 is the square root of 21. Okay. Now, oftentimes I like to use Pythagorean quadruples, you'll see on the homework. This was not one based on my drawing. And that's how you find the length of a vector. Okay, in general, I guess, if vector v is an element of Rn, which is to say that it's an n-dimensional vector, then we're going to define the length of v as the square root of the sum of the squares of the components. Okay, so we're going to let I run from 1 up to n. We're going to add the ith component of v squared. Okay, I didn't need this much. But right, we square the components, we add them up, and then we take the square root, is what that's saying. Okay, and so this is valid in 5 dimensions, 14 dimensions, 2 dimensions, even 1 dimension. Next, I'm going to talk about the dot product, which is also sometimes called the scalar product or the inner product. Okay, the thing with the dot product is that kind of the first thing I want to point out is that it takes in 2 vectors and gives you back a number after multiplying them. And multiplies is maybe a bit of a stretch for a verb, but we call it a product. So it multiplies 2 vectors and gives you a number. And somehow this scalar is a measurement simultaneously of the relative lengths of the vectors and the way that they sit. Okay, with respect to each other, like the angle. And I'll tell you more about that in a second. But how do we actually compute this? It's really simple. So if we have x equal to, we'll do a 4-dimensional vector, 1, 2, 3, 4. And y is equal to 1, 0, negative 1, 0. Then x dotted with y, we get by multiplying and adding over and over again. We take the corresponding entries, so 1 times 1 plus 2 times 0 plus 3 times negative 1 plus 4 times 0. Okay, yeah, see, I'm going to run out of room, so I'm going to slide this over. I still think I'm going to run out of room, but it'll be all right. 1 times 0, wait, no, that's 1 times 1 plus 2 times 0. Plus 3 times negative 1 plus 4 times 0. And so that's 1 minus 3 is equal to negative 2. Okay. This is defined for any type of vector, any dimension of vector. Whereas the cross product is, we're mainly going to use it for a 3-dimensional vector. So I guess, that's really all I need to tell you about the dot product for now, until I go to tell you about the angle between 2 vectors property, the cosine property. And so I'll tell you that the cross product is the one where we can multiply 2 vectors and get a vector back. So I'm just going to write that in. And it's going to return a vector. And in this course, this is always going to be a 3-dimensional vector. There are, interpretations of cross products of other dimension vectors, mainly related to the fact that the cross product doesn't just give you any old vector back. If you give it 2 vectors, like say these 2, it's going to give you a third one that's mutually perpendicular, right? Or mutually orthogonal is probably better terminology. But so if it starts here, it's going to be maybe something that comes up You can't really see very well on this. But it would come up out of the screen if these are sitting flat with, parallel to the page. And it also anti-commutes. So this one times this one, it follows the right-hand rule, so it would go up. But if you did pencil times green pen, it's going to go down into the page because it observes the right-hand rule. But that's not going to be super important for us, I don't think. At least not at this juncture of the course. What was the other thing I had to say? So A crossed with B will be the negative of B crossed with A. That's something I might let you verify on your own. Okay, and this is generally going to be, what was I going to say? Yeah, 2 3-dimensional vectors. So I'm going to just remind you how to do that. So I'll say, let's do one. The numbers won't be too bad. So U equals 2 1 2, and V equals what was I thinking? How about negative 1 0 3? I think that should keep the numbers pretty nice. Okay, and what we do with U crossed to get U crossed with V, which is itself a vector, is we're going to do that thing with, we set up a matrix with I, J, and K, where I, since I'm just starting this class and I'm not really assuming that anybody's taken physics, I is the unit vector in the x direction, J is the unit vector in the y direction, and K is the unit vector in the z direction. I think I'm going to actually come in and draw you a quick picture of the way that these sit on a scratch sheet of paper, just so I'm the most clear possible, because I realize I have not defined the unit vectors in the x, y, and z directions. Okay. When I say a unit vector, I mean a vector that has length 1. So what I'm going to do is I'm going to start in, and I'm going to just draw our traditional x, y, z axes. X, z, x, let y lay in there. All right. And so I is going to be, okay, if this right here is 1, okay, then I will be this vector right here. Okay, so what I'm going to do is I'm going to just erase all of this, make that kind of like an arrow. I'm going to label that I. Okay, J is the unit direction in the y, or the unit vector in the y direction, so we'll call that 1, and say that this is J. And then K is going to be the unit vector in the z direction. Okay. So if you just stop looking at everything else, you can see that, IJK is like that. Okay, it's not the best drawing ever. And that a given vector like 4, 0, 10, okay, can be written as 4i plus 0j plus 10k. Okay. That is a way that you might write vectors in like a physics class, but it won't be terribly useful for us because it's just like a lot to carry around instead of just writing 4, 0, 10 as a column matrix. That'll be much easier for us to work with in this class. Okay. Anyway, we write down ijk in the top row, and if we're doing u crossed with v, we got to start with u, and that does matter because unlike regular multiplication where 4 times 5 is the same as 5 times 4, u times v will be the negative of v times u, so it really does matter. So I got 2, 1, and negative 1, 0, 3. Okay. And what's going to end up happening is this is going to equal I times, okay, and then what you do is you cover up the row and the column that have I in it. And then we take the determinant of this 2 by 2 matrix, which you may not know about yet, but basically what we do is we multiply down diagonally and then the other way down diagonally, and we subtract the products. So 1 times 3 minus 2 times 0. Okay, you subtract j times the, same thing when you cover up like that. So 6 minus negative 2. the reason why it's negative j here is something that you will find out later in this course. Because really what we're doing is we're taking the determinant of a 3 by 3 matrix. But that's a different discussion. Okay, so I've got 2 times 3 minus 2 times negative 1. And then it switches to plus k times, you can barely see that, I'm kind of holding it for room on this page, but plus k times, hold on, there we go. You cover that up, 2 times 0 minus 1 times negative 1. Okay, so I've got 3, and yeah, that's going to go off the page, so I'm just going to say u crossed with v is, okay, 3, 6 plus 2 is 8, and 0 minus negative 1 is 1. Okay, so 3, 8, 1 is the cross product. Okay, maybe later on in this course I'll give you a couple of properties of the cross product, like the way that you can find the length of the product. It's related to the length of the two of these and the angle they sit at, but you know, I'll tell you more about that at a different time. That's how we cross two vectors. Alright, next we're going to talk about orthogonality. And in this course, orthogonal is, you can think of it as perpendicular. It's a more general term for perpendicular. Okay? And we're going to say by definition that vector A and vector B are orthogonal if their dot product is 0. It's that easy. If A dotted with B comes back 0. Okay. It also the dot product is also related to the vector projection, which I don't have a whole lot of need for in this course. Occasionally, I think, you know, later on we might need to talk about projections as they relate to subspaces and such. But the dot product is also related to the length of the projection. So that's just something that you could investigate if you were interested in. One thing I said was that the cross product, you know, takes two vectors in and gives you back a third vector that is orthogonal to both of the originals. So I'm actually going to just use what I just did as an example. I'm going to check the orthogonality of my cross product against my two factors. Alright, so I'm proposing that both of these are orthogonal to 381. So what I'm going to do is I'm going to just start by dotting this one and that one. Okay, so 2, 1, 2. That doesn't look right. I've made an error. Hold on just a second. This is going to need to be negative 8, right? I forgot the negative j. Let me go back and make sure that that's exactly what happened. Minus j times positive 8. Look, there it is. There you go. Minus j times positive 8. So this needs to be a negative 8. Okay, that was probably a good catch. I want to publish the video with a sign error in it. At least an unfixed sign error. Okay, so here we are. We're back here to orthogonality. And so it's going to be, and you can see that 2, 1, 2 dotted with 3, 8, 1 was not going to be able to come back 0 because there's no negativity anywhere. Okay, and if you think of two vectors with only positive entries, if you think they're both in the first octant, or you think in the two-dimensional case, if they were both positive, they'd both be in the first quadrant. And if you've got two vectors that are stuck in the first quadrant, there's no way they can be orthogonal, right? Because they don't have enough room to get orthogonal, right? You would need zeros. You need a lot of zeros. Okay, so 2, 1, 2 dotted with 3, negative 8, 1. And that's going to be 6 minus 8 plus 2, which is 0. Okay, that's good. And then negative 1, 0, 3, dotted with 3, negative 8, 1. And you can see, okay, that 0 is looking pretty promising because I got negative 3 and positive 3. Negative 3 plus 0 plus 3 equals 0. Okay, so it's true. Cross product is going to give us a thing back that if we dot it with any of the originals, we'll get 0, which means it's orthogonal. And 4, 5, 10-dimensional vectors can also be orthogonal, provided that they're dot product. And you might be wondering, I don't even know what 5 dimensions is. How can something be perpendicular in 5 dimensions? And even if it could be perpendicular or orthogonal in 5 dimensions, who even cares? And I've actually got an answer for that, and it'll come on later in the course. But not everything comes down to geometry and spaces. Is that the applications of this stuff, especially to computing and things, can make all of a sudden huge dimensional spaces really useful to analyze. Okay, but that's a discussion for later in the course. All right, so angle between two vectors. All right, now this is a theorem, and I was thinking about proving it for you in this video, but I think what I'm going to do instead is maybe I'll record a separate video for this, for the proof of this, because it's going to use the law of cosines, and if you don't really care why this is true, then I'm not going to waste your time on it. This is already, I'm over 20 minutes now, so I'm going to try to keep this one short, and I may record a separate video with the proof of this theorem. The fact is that, if you've got vector A and vector B, both in Rn. I'm not saying this is 2-dimensional, 3-dimensional. It could be 6-dimensional. Okay, there's a property that, for A and B both being the same dimension of vector, being an n-dimensional vector, it will always be the case that A dotted with B, their dot product, is equal to the length of A times the length of B times the cosine of the angle in between them. So times cosine theta. Meaning, and I don't actually like doing this, I find this pretty easy to remember. Not that, memorization is going to be a huge component of this course, but I can remember this pretty quick, and it's always easy enough to solve for theta that way, rather than remembering, because you can, right? You could say that theta was the arc whose cosine is A dotted with B divided by the length of A divided by the length of B. Whoops, that didn't go well. But this is just a little easier to work with, I think. And this is also closer to the statement of the law of cosines. That's how we find the angle between two vectors. So I think what I'll do is I'm just going to make up two 3-dimensional vectors. And how about 1, 1, 1? That's always a good one. I'll let U equal 1, 1, 1. Okay, it would probably be good for you to verify that the what am I saying? That the angle between two vectors that have like the same numbers is either 0 or 180. Okay, so I might say 1, 1, 1 dotted with 1, 1, 1. It's going to be 3. And then you'll be left to fill in the rest. You can also see 1, 1, 1 versus 2, 2, 2 would give you the same thing, right? There's no angle between those vectors. They're on the same line. So U is that. W is going to be, just a second, how about, I've got an idea where that one's going. How about up, can we just make like, oh, well, it's, in that case, it would be right angle. So let's see, 2, -1, -2, just something like that. Okay, this is not, the numbers are not going to work out nicely here. Okay, so we dot U and W, and we want to find the angle between the two vectors. But I'm saying that I'm going to suspect just real quickly try to draw one, so 1, 1, 1, right, and 2, negative 1, negative 2. Okay, so it's going to be down here. That's a very, very poor drawing, and it really looked bad on the camera, but I can understand. And you can see that there's clearly an obtuse angle here because it goes up here and then it goes down there. And what's going to happen is that anytime these two dot to a negative number, so u dotted with w, is going to be 2 minus 1 minus 2 is equal to negative 1. But that makes sense, right? Because the length of a vector is always positive. So if the dot product is negative, cosine of theta has got to be negative. And if cosine theta is negative, it means there's an obtuse angle. Okay. And I tried to pick numbers that would give me something I could draw you a picture of, but it just didn't work out this time. So, and 1 is the length of u, so that's the square root of 3, times w. Wow, if I'd have chosen this right, I could have made this a 30, 60, 90 triangle, or like an actual one that I could have solved for our cosine. That would have been nice. And so 2, 4, 8, 9. Okay, so square root of 9 is 3. 3 root 3. Okay. Times the cosine of the angle in between them. Yeah, see, it's so close. But that means that cosine of theta is equal to negative 1 over the square root of 3 times 3, which I'm pretty sure there's some way that we could, write this nicer, but who cares, right? I'm going to go over here and in degree mode, it's true, I am working in degree mode, very rare, but I'm going to take inverse cosine of negative 1 divided by 3 divided by the square root of 3. Okay, and dividing by both times, if you don't believe me, then you could just use more parentheses, or maybe you have a fancier calculator and you could use a fraction bar. It works. And this is how we used to have to do it when we did kind of the dimensional analysis problems in chemistry, and this was the only calculator we had. We had to put anything that was in the denominator underneath the divided by sign, and it seemed really off at first, but it's the way that the calculator thinks. So I got a 101 degree angle, and for now, the nearest degree will be fine. Okay, and that makes sense. Okay, let's see if there's any, normal vector to a plane. Yes, let's do that. It's going to be a long video. All right, so I took a break there for a second. Catching back up, normal vector to a plane. Okay, so in this class, normal means orthogonal, means perpendicular, same thing. So you got yourself a plane, right? Maybe like this. Okay. Well, it's got some tilt to it, right? And there should be a way for us to kind of standardize the amount of tilt of a plane in the way that we have standardized, like, say, the slope of a line. But if you think about it, then we're reduced to saying, okay, well, we could talk about the angle it makes with the positive z-axis or something like that. But even that can be a little ambiguous because, does it intersect the z-axis coming down or going up as we look at it from our standard perspective? Who knows? We don't really know. This is just some plane that I drew for you. So what can really kind of anchor the plane in terms of its direction is a vector that comes out of it, a normal vector, like an orthogonal vector to the plane. So I think, how would I want to draw this best? I think what I'm going to do is I'm going to maybe just say, suppose it's straight up. Is that how I'm supposed to draw this? I don't know. And then definitely parallel, though, to the parallelogram representing the plane. Okay, so you see, I'm trying to indicate that this is a vector that is normal to the plane. Okay, and it is really as simple as for a plane ax plus by plus cz plus d equals 0, or equals d, or there's some constant term. It's ABC is the normal vector. The normal vector, which we'll generally, is going to be A, B, and C. And you're going to be like, wait a second, dude, that seems too good to be true. Like, that we don't just pull the slope off of the numbers from X and Y. And that's true. It's a little more complicated than that. But what I'm going to show you is that, like, let's just talk about some y equals mx plus b type of line. How about we do this one, the one that connects these 2 points, this line. I think this will be a good example. This is going to be y is equal to 1.5x plus 3. Okay, but notice we solve for y. And over here we're looking at the standard form, but we can write this in ax plus by equals c very easily, right? I could say, if I wanted to, just write this as ax plus by equals c, I could say 3x plus 6y, wait, not plus, right? It's going to need to be a minus. 3x minus 6y equals negative 6. What have I done? Okay, just to be clear, I'm multiplying everything by 2 here to get rid of that denominator, so that would definitely be a 2y. And this would be negative 6. Okay, and just to check, our intercept is y equals 3, yes, and x equals negative 2. Okay, there we go. So let's talk about the vector 3, negative 2. 1, 2, 3, negative 2. It's kind of a vector right here, right? But if we were to extend this, notice it's going to be, even in my very poor drawing, it's going to be pretty much perpendicular. So that's why it works, is it has been happening all along in the two-dimensional case. It's just we're so used to y equals mx plus b, and we don't usually use ax plus by equals c except in algebra 1, or when we want to eliminate, or when we want to just really easily write down the intercepts. Okay, but this has been happening all along. Now, I think what I need to tell you, like okay, you told me that there's a normal vector, but who cares? So, point normal form for a plane. This is going to be the best way of writing down the equation of a plane, right? So if we've got a point P, I'm going to actually call it Q because sometimes P is for plane, right? So I've got point Q, which is A, B, C, and normal vector, say, and 1, and 2, and 3. Well, then, and if I've got a point and a normal, then I've really just defined the plane as the set of all vectors that are starting from Q, and they're, the vector itself is orthogonal to n. Okay. And I'll just let you think about that for a second. But if I've got a point and a normal, I've pretty much got a whole plane defined. That was actually a pretty decent drawing. So, except for the normal didn't really come out of the point, but it's all right. So what we're going to do is, remember, the normal is like kind of the slope numbers. So it's n1 times x minus a plus n2 times y minus b plus n3 times z minus c. And in retrospect, I kind of wish I'd call that x0, y0, and z0, but and that's going to equal 0. And you might be like, wait, where'd that ax plus zy, or ax plus by plus cz equals d, where'd the d go? And it's like, well, it's kind of included in this n times negative a1, and 2 times negative b, and 3 times negative c. It's like, it's there, but that's how we're going to write it. Kind of like y minus y0 is equal to the slope times x minus x0. There's no some other constant. The constant that comes in y equals mx plus b is just like kind of combined by those. So I think that, you know, there's going to be some problems on this classwork that are going to be a little more involved on this normal plane stuff, just to give you some of the problems I couldn't give you on the first day. But otherwise, you know, the rest of the things, it should be very, very direct and straightforward. Just some things I need to remind you of before we start moving and talking for a whole semester about vectors and planes and lines and stuff. So there you go.